Hello everyone, and welcome back to our series on sorting algorithms. I'm not going to beat around the bush. Today we will be covering one of the most infamous algorithms out there, the appropriately titled QuickSort. Now, because QuickSort is one of the most efficient algorithms out there, it's also one of the more complicated as well. So let's jump straight into it, since we have a lot to cover. Starting with the definition. We can define QuickSort as an efficient, in-place, divide and conquer algorithm which sorts elements by partitioning the dataset into two parts, then recursively sorting each side independently. This continues until we have a sorted list. To partition the dataset into two halves, we use what's known as a pivot, which will help us categorize the data so that it's easier to sort. If you are unfamiliar with recursive divide and conquer algorithms, then I highly recommend you check out our video on MergeSort, since that gives a pretty good introduction to some of the concepts that we'll be covering today. To give you a robust example of how this partitioning concept is carried out, let's pull up a shuffled array containing the first 12 letters of the alphabet. Our first step is to pick a pivot element. This is an element around which all other data points will be partitioned. For the sake of this example, I'm going to choose the letter E. Now, an important characteristic of the pivot is that it will always end up in its correct sorted place in the list. So, since E is our pivot, let's place it at its correct place in the list, or at the fourth element. For now, let's just swap the element that was at the fourth index and place it where the letter E was. Okay, so now that we have our pivot in the correct place, we can move on to the next step. What we do next is partition the array into two sections, with all letters less than the pivot going on the left side of the pivot, and all letters greater than the pivot element going on the right side of the pivot. Notice how these two sub-datasets are not sorted by any means, they're just categorized in such a way where any particular element to the left of the pivot is a letter less than E, and vice versa for the right side. The actual sorting will come later, when we recursively call QuickSort on the left and right sides of the dataset. That's how we'll eventually get the list to be sorted. The partitioning process represents an overview of what QuickSort looks like. However, it leaves out quite a few important questions, such as how do we determine the pivot? How do we rearrange elements to be less than or greater than the pivot? And how do we recursively sort the sublists? All of these are valid questions which will get answered during the latter part of this video. Before that though, I want to dig a little deeper into the actual partitioning process, and go over the concepts definitively rather than just conceptually. The reason I'm going to do this is because the entire concept of QuickSort is hinged on this idea of partitioning the dataset into two parts, and so having a thorough understanding of the process is extremely important. Okay, so the basic idea of partitioning the dataset is represented by a set of three conditions which must be met, and they are as follows. Number 1. An element J is in its final correct position in the dataset. This condition describes the pivot which we mentioned earlier. In order to split the list into two parts, we need a pivot to serve as the partitioner, and so it makes sense that that element would be in its correct place in the list. Once we have this, we can separate the elements into either less than or greater than this pivot. Stipulation number 2 is that no element from the lower bounds of the dataset through to the element just before the pivot is greater than the pivot element. And stipulation 3 is that no element from just above the pivot element through to the higher bound of the dataset is less than the pivot element. These last two conditions describe the actual rules for the partition that were shown earlier during our robust example. You can see this much more clearly if we bring up a list of 10 elements that are partitioned correctly around the fifth. We can color code the left and right half of the dataset accordingly, as well as the pivot, to show all three conditions of the partitioning process in full effect. You'll see that from the lower bound of the dataset through to the element just before the pivot, no element is greater than the pivot element. Additionally, the pivot is in its correct sorted place in the list. And finally, from the element just above the pivot through to the higher bound of the dataset, no element is less than the pivot element. These three conditions are what describe a successful partition. The problem then becomes how we achieve this state. Of course, once we're here, we can simply recursively call the QuickSort function on smaller and smaller portions of the list, similar to how we sorted a list using MergeSort. But getting here is the tough part. In order to get from a non-partitioned list into a partitioned list, we use what's known as a partitioning method. I know, computer scientists coming in clutch with another outstanding and creative name. Either way, the partitioning method is a separate function in computer science, much like how the merge function was separate from the MergeSort function. This means that it will be externally called from the QuickSort function. Now, because it is a function, that means it obviously has pseudocode. So, right now, we're going to go over the partition pseudocode, as well as a quick example, so that way we'll be able to talk about the QuickSort pseudocode through and through without gaps. Okay, let's begin. The first thing to mention is that we take in two arguments into the partition function. These being low, or the index of the lowest element in the list or sublist, and high, the index of the highest element in the list or sublist. These will be determined by the QuickSort function and then passed into the partition method. As for the actual pseudocode, we begin by arbitrarily choosing a pivot index. This is the index location of the element that will be placed in its correct sorted location at the end of the partition. The element we choose to be our pivot doesn't really matter since the list is going to be randomized, but there are a few lines of thinking. These include always picking the first element as the pivot, always picking the last element as the pivot, picking a random element as the pivot, or picking the median element as the pivot. There aren't any major differences in which methodology you choose, but for the sake of simplicity, we'll go with the second option, which is picking the last element. We store this in an integer, bringing our total number of variables to 3. Now, we move on to the actual partitioning process. We need a way to position the data in such a way where elements less than the pivot element end up on the lower end of the pivot, and elements greater than the pivot element end up on the higher end of the pivot. The way we do this is a bit complicated, but it involves the two variables which we passed into the function, low and high. From these two variables, we can define integers low index and high index. These are, of course, indexing variables, meaning we'll be using them to traverse across the dataset and make changes to the list accordingly. Now, low index will start from the leftmost index of the dataset, which is stored in the low integer, and high index will be the rightmost index of the dataset, excluding the pivot. This can be found by subtracting 1 from the high integer. We don't want to start looping from the highest index, since that's where our pivot is stored. Okay, so we have our pivot index and our traversing index variables, all initialized to indexes of the dataset. We then enter a while loop. The condition for this while loop is while true, which might not make too much sense. True is always true, and you'd be correct in that statement. What this basically means in the context of our partition method is that we want to run the code inside of this while loop until we reach an exit case. This will be some property such as a value being greater than another value, or a Boolean expression being equal to false, etc., etc. Once the exit case is hit, we run what's known as a break statement, which will break us out of this external while loop. I'll explain further once we actually reach the exit case for this particular while loop, but for now just note that the instructions inside of this loop will run as many times as we need them to. We then move into a set of two while loops. These while loops will take us from the low index going up and the high index going down, which means that eventually the two while loops will converge upon each other. In the first loop, we loop until the element at the low index is less than the element at the pivot index, increasing the low index within the loop. This essentially translates to increasing the low index until we arrive at an element that is greater than or equal to the pivot element. Why do we do this? Well, because again, we're trying to partition the list around the pivot so that elements less than it are on the lower side of the list, and vice versa for the upper side of the list. As long as elements on the lower half of the list are less than the pivot, we really don't care about them, because they're already on the correct side of the partition. Now what we do care about are elements on the lower side of the list that are greater than or equal to the pivot, since those need to be placed on the other side. So, once we have an element that is greater than the pivot element, we exit the loop, since we have found an element that needs to be moved. The second while loop, as you'll see extremely shortly, will work on finding a partner for this out-of-place element, so that we can swap them. In the second loop, we loop while the element at the high index is greater than the pivot element, and while the high index is greater than 0. Of course, then, inside this while loop, we decrease the high index. Again, the first part of the statement has us looping down from the top of the list until we find an element that is supposed to be on the low half of the pivot, but is not. This will be the partner element to the one we just found in the lower loop. Also, the second part of the statement is simply a check to make sure we aren't going out of bounds. If we ever get to a point in the list where the element at the high index will never reach an element less than the pivot, then this will stop it at the beginning of the list, helping us avoid an out-of-bounds error. Now the final question we ask is if the low index is greater than or equal to the high index. This is basically asking us whether or not the two indexes have converged upon each other. If the low index ends up being greater than or equal to the high index, then we know that the two have met at some point in the list or sublist, and all elements left and right of the pivot have been checked to make sure that they're in their respective locations. This indicates that we are ready to finish partitioning the list, since all elements will be on the correct half of the dataset. Another note is that this is the exit case I talked about at the beginning of the pseudocode. Once the low index is greater than or equal to the high index, we can be assured that the partition has been completed and exit out of the loop using a break statement. Until then, however, we repeat these two while loops until this condition is satisfied. Okay, so if this statement is true, then we break out of the outer while statement. But if this statement is false, then we've ended up in the situation that we've been building towards this entire time. We have an element that is greater than the pivot stuck on the low side of the dataset, and an element that is less than the pivot stuck on the high side of the dataset. Both of these elements are not on the right side of the list, and so what do? Well, it's obvious. We swap them. Hopefully the puzzle pieces are connecting now. The entire point of the while statements encased within the outer loop was to find two elements that were not in the right place so that we could swap them accordingly. This allows us to easily and efficiently partition the dataset so that it follows the rules we laid out earlier for a successful partition. And so, after that if statement has concluded, we exit out of the outer while loop. Now, we have one final statement which ties the whole thing together. We first swap the element at the low index with the element at the pivot index. This is what completes our successful partition, as it does two things. First, it places the pivot in its correct spot in the list, satisfying our first condition for a successful partition. And second, it places the last element that's greater than the pivot on the high side of the partition. You might be wondering why we swap the element at the low index with the pivot, and that's simply because the last element that the low index is stopped on will always be greater than the pivot, simply because of the way that the loop is set up. And also, that index will always end up at the correct location of the pivot because of the way that the counting works out. Swapping that element with the pivot element, which again is at the last element in the dataset, ensures that our rules for a successful partition are followed to a T. Now you might be thinking that's it for our pseudocode, but you'd actually be wrong. The last thing we do before exiting the code is return the low index back to the user. That's right, the partition function is actually not a void function. If you're unfamiliar with functions and return types, then I'd recommend you check out that portion of our Introduction to Programming series, which will be linked in the description below, as well as in a card in the top right corner. The basic gist of it, however, is that we return the index location of the pivot, which is now located at the low index, back to the user. The reason we do this will be explained during the pseudocode for QuickSort, but essentially it's so that we know where we need to divide the list so that we can recursively call the QuickSort function on both halves of it. So there it is, the complete pseudocode for a successful partition. I tried to go as in-depth as possible here, especially considering the popularity and efficacy of the algorithm in computer science. but feel free to ask any questions you may be left with in the comments below. Okay, now that we have the pseudocode down, let's work an example. I'm going to pull up a list of 8 elements, unsorted, and instead of actually sorting the algorithm just yet, we're just going to focus on partitioning the dataset so that it follows our rules for a successful partition. As a reminder, those are A, an element j is in its final correct position in the dataset, B, no element from the lower bound of the dataset through to the element just before the pivot is greater than the pivot element, and C, no element from the element just above the pivot through to the higher bound of the dataset is less than the pivot element. Let's start with our pseudocode. Now, like I mentioned previously, the low and high indexes are all passed into the partition function by the QuickSort function, but we can pretty easily determine them through intuition. The low index will be the lowest index in the dataset, or 0, and the high index will be the highest index in the dataset, or 7. We then define our pivot as the highest index in the dataset, so 7. Up next, we set up our traversing indexes. So low index gets set equal to the low index which was passed in, and high index gets set equal to the high index which was passed in minus 1. This makes the traversing indexes 0 and 6 respectively. Before we enter our outer while loop, let's color code all 3 important indexes on our array: the low index, high index, and pivot. The next step is to enter our while loop. This will run indefinitely until we reach our exit case, which again will come later when the low index is greater than or equal to the high index. Inside of this while loop, we begin with what I'll call the low loop, in which we increase the low index until we hit an element which is greater than the pivot. So, if you look, the first element at the low index is not greater than the element at the pivot index. This means that it's already on the correct side of the partition, and we can increase the low index to 1. Now the second element, the one at the first index, is greater than the pivot. This means that it is not on the correct side of the partition, and so we can exit the low loop here. We then immediately enter what I'll call our high loop to find an element to swap with the one we just stopped at in the low loop. So we check the element at the high index, which is 8. Now 8 is not less than the pivot element, and so we decrease the high index. After that, the element at the high index, 5, is still not less than the pivot element, and so we decrease the high index again. Finally, we reach the fourth index, which contains the integer 3. The integer 3 is less than the pivot element, and so we have found our pair of elements that need to be swapped. If you remember back to the pseudocode, I described it like this. The integer 7 is on the low half of the list, but it should be on the high half of the list. And the integer 3 is on the high half of the list, but it should be on the low half of the list. And so we need to swap them. First though, we check to see if the low index is greater than the high index, which it is not. And so we are good to swap the elements contained at the low and high indexes. Now we simply repeat this process again. We go all the way back to the low loop and start comparing elements. Since the element at the low index, 3, is less than the pivot element, we increase the low index to 2, and get lucky, since the element contained there, 9, is greater than the pivot element. We can now exit the low loop and move on to the high loop. Here, since 7 is greater than the element at the pivot, we decrease the high index to 3, and again get lucky, since the element there, 1, is less than the pivot element. We have found our second pair of elements to swap. We first check again to make sure that the low index isn't now greater than or equal to the high index, and once we confirm that it isn't, we're good to swap the elements at the low and high indexes. Now since the low index wasn't greater than the high index, we haven't yet reached our exit case. And so we go back to the beginning and run through our 2 while loops again. Since the element at the low index, 1, isn't greater than the element at the pivot index, we increase the low index to 3, which coincidentally is also currently where the high index is at. When this happens, we'll color the cell a nice light green color. The element at this index, 9, is greater than the element at the pivot, and so we're okay to exit the low loop now. Moving straight into the high loop, since 9 is greater than the pivot element 4, we decrease the high index and find the element at that index, 1, is less than the pivot element. And so we found our pair of elements. What's different this time, however, is that the low index is now greater than the high index. This indicates that we've covered all elements in the dataset and positioned them in such a way where we'll now be able to swap the pivot element with the element at the low index, and the list will be partitioned correctly. And since we've reached our exit case, that's exactly what we do. We break out of the outer while loop and swap the element at the low index with the element at the pivot. We have now successfully partitioned a list of 8 elements. You can see that 2, 3, and 1 are all less than the pivot element, and 7, 5, 8, and 9 are all greater than the pivot element. This is the main strategy that's implemented in QuickSort, and also the backbone of how it takes an unsorted list and turns it into a sorted one. You might be asking yourself how this helps us get an unsorted list into a sorted one, since we never actually care about the order of the elements, and the answer to your question is of course everyone's favorite computer science methodology, recursion. Recursion is a very useful but very complicated topic in computer science, and unfortunately, a basic understanding of it is needed to fully comprehend QuickSort. Luckily enough for you, we've covered recursion before in our Introduction to Programming lecture, and so a link in the description or a card in the top right corner will take you to that portion of the video. With that being said, now that we have the power of recursion and partitioning on our side, we are ready to jump straight into the pseudocode for QuickSort. Now the first thing to mention about the pseudocode for QuickSort is that we also pass in 2 values into the function, similar to the partition function. The first is the starting index, which I'll call low, and the second is the ending index, which I'll call high. These 2 values should look familiar, but we'll be using them for different purposes than we did in the partition pseudocode. Now for our first pass through the pseudocode, these 2 values will be hard-coded, with 0 serving as the low index and the size of the array -1 serving as the high index. For each recursive subcall, however, the low and high values will be calculated by the computer, so keep that in mind as we work our way through the pseudocode. The first step in our QuickSort pseudocode is an if statement, asking whether the low index is less than the high index. This is what's known as our recursive base case. Once this condition is no longer met, we can break out of the recursive subcalls. As you might be able to infer, this if statement will only become false when the low value is equal to the high value, in which case we are trying to perform a quicksort on a dataset with 1 element. So, essentially what this statement is saying is that we want to keep recursively calling quicksort on smaller and smaller lists until we reach a point where the low and high indexes are equal to each other. Now, if this if statement is true, then we know that we still have lists that needs to be partitioned, and so we need to call quicksort on the low and high halves of the list respectively. What we need first, however, is the index location of the pivot. This is so that once the list is partitioned, we know where the list is partitioned around so that we can recursively call quicksort on the elements below and above it. The way we get this, as you might have guessed, is through the partition function. We mentioned before that the partition function was actually a returning function, meaning that at the end of it, we return the index of the pivot. As you can see, this return variable gets set equal to the pivot variable. So after the partition function concludes, what do we have? Well, for starters, we have a correctly partitioned list thanks to the partition function. We also have the index location of the pivot, which partitions the array into 2 sections. And finally, we have indexes representing the lowest and highest index locations in the particular dataset that were passed into this quicksort call. The next step is to recursively call the quicksort method on the low and high halves of the list. This is fairly simple, as we just call quicksort twice. For the first call, we pass in low as the low index and pivot -1 as the high index. And for the second call, we pass in pivot +1 as the low index and high as the high index. Now notice how we skipped over the actual partition index, passing in locations one below and above it instead. This is because the element at the partition index is already sorted. It was placed in its correct sorted location during the partition method called above, so we don't need to worry about it when recursively calling our QuickSort methods. After ending the if statement, believe it or not, that's the entire pseudocode for QuickSort. The majority of the actual sorting occurs during this partition method, which we went over already. The actual QuickSort method is simply there to piece everything together using recursion and some computer science duct tape. Another thing you might notice is that this algorithm looks oddly similar to MergeSort. We do some calculations, recursively call the function, and somewhere in the mix reference a separate function to do the dirty work for the algorithm. This isn't just a coincidence. QuickSort, like MergeSort, is a divide and conquer algorithm, which makes it so that the algorithms are quite similar in structure. Okay, so now that we know how QuickSort works and how the partition method works, let's jump into an example QuickSort. We first pull up a list of 8 elements. In this case, low is going to be 0 and high is going to be 7. We get these values from the size of the dataset being passed in. 0 is obviously the leftmost index, and 7 is the rightmost index. Now the low index is less than the high index, which means we haven't yet reached our base case for the pseudocode, and we enter the if statement. The first thing we do is set pivot, or the partitioning index, equal to the result of a partition of the dataset from the low index to the high index. Now we just went over how to partition a dataset of 8 elements. These exact 8 elements as well, in the exact same order to boot. So I'm just going to take some executive authority and instantly get the list in the state that it was at the end of our partition example. If you missed that, you can use the timestamps in the description to see how we got here. So now that we have this basic list partitioned around the third index, what we do next is recursively quicksort the left and right halves of the dataset. So we'll be quicksorting the sublist from the 0th index to the 2nd, and from the 4th index to the 7th. Beginning with the left half of the list, we update our low and high values to represent the index numbers that were passed in. This makes them 0 and 2 respectively. If you're confused about how we got these numbers, simply look at the line of pseudocode on your screen now. Low was obtained through the original quicksort call, with it being 0, and high was obtained by subtracting 1 from the pivot index, which was 3, making it 2. Now the first thing we check is of course if low is less than high. This is our base case, and if this is false, then we can exit out of this recursive subcall and go back up the chain. Unfortunately for us, this is not the case, as 0 is not less than 2, at least on Earth, and so we soldier on. The next step is to partition the list into 2 more sublists using the partition method. If you remember, that entails setting up our 3 indexes: low index, high index, and pivot. Luckily enough for us, we have exactly 3 elements, in which each one corresponds to one of those 3 indexes. Low index is 0, pivot is the highest index, or 2, and high index is 1 minus the pivot index, so 1. Now that we have everything set up, we move into our low loop. Since the element at the low index is less than the pivot, we can immediately exit the low loop and move into our high loop. The element at the high index is not less than the pivot, and so we decrease the high index by 1, making it 0. Now here's where the second part of that while statement comes into play. If we bring it up on your screen now, you'll see that we have the condition, which is that high index is greater than 0. Well, in this case, high index is 0. 0 is not greater than 0, and so this is actually an exit case for the high loop. This means that we can exit out of the high loop, and coincidentally also the outer while loop, since we've reached our break case. Low index is no longer less than high index, since it's equal to high index. This allows us to break out of the loop and conclude with the final 2 steps of this partition. The first of these is to obviously swap the element at the low index with the pivot index, which we do, and then finally we return the low index back to this particular quicksort call so that we can recursively sort the low and high halves of this list. What this entails is quicksorting the left half of the list, which is just the element 1, and quicksorting the right half of the list, which are the elements 3 and 2. Now I'll save you the trouble on the left half here. Since the pivot index is 0, we'll be sorting from the low index passed into this quicksort function, which is 0, to the index just below the pivot index, which is -1. This will immediately trigger the base case and end up just returning back up, so we don't need to waste time going through that. On the right side, however, we'll need to do some work, since the low index will end up being 1 plus the pivot index, which is 1, and the high index will end up being the high index passed into this quicksort function, which is 2. Now in the interest of time, the recursive call on the right side of the list will basically take a lot of instructions to simply do one thing, and that's swap 3 with the pivot index, which is 2, and return the index location 2 back to the user. This will be the case any time that we call a quicksort on a list with 2 elements, and since this video is already going to be quite long, we'll gloss over these parts in the future. Additionally, since these sublists now only contain 1 element, they're also considered sorted, and we can move on. When we do move on, we move on to the right side of the list, which you'll notice has remained dormant this entire time. This is something you'll see especially in the visualization, but when using quicksort like this, we first have to sort all the left half recursive paths before we even begin to work on the right half path at all. So essentially what this means is that the entire left half of the list becomes sorted before we even start on the right half. Beginning with the right half finally, we first have to update our low and high variables, as this is a new recursive quicksort call. Low becomes 1 plus the pivot index, which makes it 4, and high is just high, meaning it stays at 7. Then we check if low is less than high. Our base case is true, which means we need to do some additional sorting on this right side. We begin by partitioning this dataset, which calls for another run through the partition function. We start by setting up our traversing indexes. The low index is the same as the low integer, which was passed into the function, and the high index is 1 minus the high integer passed into the function, and of course the pivot is just the high integer passed into the function. Now it's time to find our elements, so we start in the low loop and check 7 against the pivot. Since 7 is less than the pivot, we increase the low index, because, remember, we're trying to find an element that's higher than the pivot. So we increase the low index and test the integer at this new location. 5 is still not greater than 9, and so we increase the low index again. The element here, 8, is still not greater than 9, and so we increase the low index one more time, which brings it to the pivot. This time, the element here, 9, is not greater than the pivot, but it's equal to the pivot, which still satisfies our test condition, and so we stop the low index here. This is an example of another failsafe in quicksort. We make the condition for the while loop be while the element at the low index is less than the pivot, because eventually, if we keep increasing the low index without finding a suitable element that's less than the pivot, we'll eventually reach the pivot, in which case we can exit out of the low loop. Okay, so next we start out at the high index and test that against the pivot. That element is less than the pivot, and so we immediately exit the high loop. Additionally, since the low index is greater than the high index, we can exit our partition already. We swap the element at the low index with the pivot, which changes nothing, and return the low index back to be the pivot of the next 2 quicksort calls. We start with quicksorting the left half of the dataset, which runs from the low index passed into this quicksort call to the element just below the pivot. Updating our low and high values gives us 4 and 6, which is the sublist containing the integers 7, 5, and 8. This quicksort call starts with yet another partition, with 7 as the low index, 5 as the high index, and 8 as the pivot. Again, we get these values from the pivot index from the previous quicksort call, as well as the 2 integers that were passed into that quicksort call. Beginning with the low loop, the element at the low index, 7, is less than the pivot element, and so we increase the low index. The element there, 5, is still lower than the pivot element, and so we increase the low index again. This time, the element at the low index is equal to the pivot element, allowing us to exit out of our low loop. In the high loop, the first element 5 is already less than the pivot, so we exit out of it immediately. We then see that the low index is greater than the high index, and so we swap the low index with the pivot, which again does nothing since they're the same, and return the low index back to the user. Now we have one final recursive quicksort run to call. This time it will be from the low index of 4 to the high index of 5, meaning the integers 7 and 5. If you remember back to the other time we had a list of 2 elements, we saved a bunch of time by realizing that the code will simply swap the 2 values, and that's exactly what will happen here. The integers 7 and 5 will get swapped, and then our quicksort will be complete, returning 5 as the pivot index. You'll notice that we never actually went through what happens with the 9 and 8 integers, since there will be recursive subcalls on them. But to keep things brief, I skipped over them for the same reason that I skipped over the one element subcalls on the other side of the list. These will immediately return back up due to the exit case of the low integer being equal to the high integer, and we won't have to evaluate anything. You might also notice that the list is a little fragmented right now, and it's honestly hard to look at. In actuality, quicksort is run in place, meaning that these extra datasets that I've made don't actually exist. They're just there to show things off a little better. We can get the actual list by taking the furthest down element for each index location. Consolidating that information on the original list leaves us with the sorted dataset. Perfect. We can delete the extraneous arrays that we used and admire the complete list in all its glory. As I've mentioned a few times already, quicksort is fairly complicated, so feel free to rewatch this segment back using the timestamps in the description below. Next up, however, we're going to take a look at how quicksort works on the large scale using the visualizer. If we pull up a smaller list of elements, you can see quicksort really go to work. Notice the clear partition between upper and lower elements that starts to appear. Then this happens again on smaller and smaller sublists until the entire thing is sorted. If we go a bit bigger with our dataset, you can really start to see things rolling. Another thing you'll notice is, just like I mentioned during the example sort, we sort the entire left side of the initial partition before even touching the right side. This is a result of the pseudocode always calling quicksort on the left half of the list first, and then the right side. Okay, so now that we know an ample amount about quicksort and how it works in both practice on a small scale as well as in a large scale visualization, we can finally jump into its time complexity equations. Quicksort's best and average case scenario time complexity equations are O of n log n, and its worst case scenario time complexity equation is O of n squared. These are determined through some pretty complicated mathematics which are beyond the scope of the series, so we won't be covering it here. Additionally, the worst case scenario space complexity equation for quicksort is O log n. Now this is something that I will be covering. Nowhere in the actual algorithm do we allocate any extraneous memory for the data, so where does this auxiliary memory come from? Well, the answer is recursion. For each recursive quicksort call that we make, it's added to the stack, which you can learn about through our data structures video. This space on the stack is included in the calculation for extraneous memory, which is why we have a space complexity equation of O log n, despite the fact that no extraneous memory was created. Bringing the time complexity equations back up, another thing you might be wondering is why these equations look slower than the MergeSort equations. Pulling them up side by side, you can see that in the worst case scenario, MergeSort is actually faster and equal in all other cases. What gives? I thought quicksort was supposed to be the magnum opus of all sorting algorithms. Well, there's actually two problems with that statement. The first is that there is no end-all be-all magnum opus for sorting algorithms. Each of them have their own strengths and weaknesses. If there was only one god-tier sorting algorithm, we would only have to learn about that one algorithm, which would be incredibly useful and also make my job obsolete. So let's not humor that idea any longer. The second misconception is that MergeSort is not overall better than QuickSort. This one has to do with the fact that the time complexity equations don't show the full story. Don't get me wrong, these two algorithms are the top of their class in sorting. If we were to make an NBA comparison, it's like the debate between Michael Jordan and LeBron James. There are arguments to be made for both of them. So, let's do a little arguing then, in a game I like to call Strengths and Weaknesses. Now, MergeSort has a worst-case scenario time complexity equation of O of n log n, meaning it's faster in the worst-case scenario compared to QuickSort's O of n squared. MergeSort requires more additional memory to help sort the dataset, while QuickSort requires less additional memory. MergeSort is scalable and can be run on both large and small datasets, while QuickSort gets inefficient the larger the dataset you try to perform it on. MergeSort is slower on small datasets, while QuickSort is, on average, faster on small datasets. And finally, MergeSort is stable, while QuickSort is not stable. So you can see what I mean when I say that these two are at the top of their class, but debates can be made for both. Say you need to implement a sorting algorithm on a dataset, which could be 10 elements or a billion elements. Well, in that case you'd go with MergeSort. How about an algorithm that needs to be extremely fast for a small amount of data? Well, that'd be QuickSort. The examples could go on and on. Both of these algorithms are extremely useful and are implemented in a lot of database scenarios, which leads us straight into our final segment, common implementations of QuickSort. Now, I don't have too much to say here, which is actually the opposite of a bad thing. That's simply because QuickSort can be implemented pretty much anywhere. Many databases use QuickSort internally, and you can find it in use amongst many of the top tech companies out there simply because of how good it is. I mean, they don't call it QuickSort for no reason. Now, if we're going based on its comparison to MergeSort, I guess you could say that it's optimal for small databases which need to be sorted fast and with little extraneous memory. This also doesn't take into account the fact that because QuickSort is so heavily used, you can guarantee that it's a heavy topic for job interviews. Questions such as how does the partition method in a QuickSort work, or how do we determine which element to use as the pivot for a QuickSort, or what are the advantages to using QuickSort over MergeSort and vice versa, are all questions that I could see being asked in a job interview to test your knowledge of algorithms. Luckily enough for you, you've just concluded a 45-minute video made by an 18-year-old talking about it, and so based on my calculations, you should be more than well equipped to tackle these questions. And with that, we are now finally ready to move on to our conclusion. To review, QuickSort is an efficient, in-place, divide-and-conquer algorithm which sorts elements by partitioning the dataset into two parts, and then recursively sorting each part independently. If you are still unsure about any of the information covered in this video, you could use the timestamps in the description below to go back to any previous section and re-watch it. Additionally, included in the description are all of the resources that I used to help write the script for this lecture, which can provide a different perspective on things if you're still confused. And finally, if you are still unsure about something, you can always leave a comment down below, and I'll try to help you out. With that being said, I have nothing else to cover. Thank you so much for watching, and I'll see you next time, where we'll be covering bitonic sort.